Okay, let's briefly talk about the new things, SDMA. As you see in this picture probably gives you a good idea. So far, okay, everyone assumes and everyone thinks that the base station will always use omnidirectional antenna. What is omnidirectional antenna? What does it mean? Your radiation from the antenna is like all around every angle, every direction. That's omnidirection, right? It is true actually. However, these days, if you go around it, right, and look at the base station, then always you see that the base station has multiple antennas these days. Okay? I don't know, maybe you can walk around, maybe you are interested in finding out. In fact, in this building, if you go to the roof, right, then you will see a base station. There is a base station. Okay? To see that, of course, you have to go out and see it, right? Then you see the base station. And that base station has multiple antennas. You probably won't see the antenna. You probably see a white box. That is antenna, actually. You have 2 here, 2 here, 2 here. You have 3, 3, 3, maybe 9 antennas or something. Multiple antennas, right? Anyway, that's because of sectoring and things like that. But anyway, when you have a multiple antennas at the base station, now using those multiple antennas, what you can do is then you can make a beam. Okay? Using the multiple antennas, you can make a beam. When you have a single antenna, then radiation will be omnidirectional. Unless you use horn antenna. Okay? Let's say you use just regular dipole type of antenna, the radiation will be omnidirectional. However, if you put the multiple of them, each one is omnidirectional, but when you put the multiple of them as an array, okay, you can actually make a beam in a certain direction. And even that, not even that, more than that, you can actually steer the beam. You can make a beam into the certain direction that you want. That is possible. Easy, actually. So that's the kind of concept of the SDMA. Why do you want to do that? What is the fundamental idea of this SDMA? Okay? The basic idea of SDMA is like this. Now we have a base station. There are users here, 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 right? Let's say base station wants to transmit some information to the user 1. Okay? Let's say this one wants to communicate with the user 1. When this base station uses omnidirectional antenna, then user 1, this base station transmit the signal omnidirectional way. Okay? Some of them will be delivered to user 1, but since this guy transmit omnidirectional way, that signal also goes to user 2, also goes to user 3, which can be a little bit unnecessary, right? So what the SDMA tries to do is that, why not just make a beam? When I transmit the user 1's data, you want to make a beam into this direction. When you make a beam, actually, then compared to the omnidirectional transmission, when you make a beam, you can actually focus all of your energy into this direction so that you can actually make a strong signal onto that direction. Compared to the omnidirectional, when you make a beam, right, you are focusing every energy onto that direction. So therefore, you have a strong signal into that direction. Okay? So that's actually better if you can do it. Right? Focusing all the energy. Because that's a signal for him anyway. Right? It doesn't have to go the other way, right? Other users. And not only that, what is even more is that when you're focusing all of the energy to him, then you can possibly make that for this direction, you can have 0 energy. That's actually important. Why is that? But that means no interference to him, right? In fact, that's actually a little bit tricky because even though when you make a beam like this is called a main beam. We call that as a main beam. When you have a main beam or main lobe, there will be always a side lobe. Okay? Because of the side lobe, there is some remaining interference into this direction or to this direction. However, there's some angle, there's some point which has null value, right? There's a certain angle that you have a null value. That is the angle that you have a zero interference. So what you need to do is that basically what the SDMA tried to do is that you want to focus your angle of your direction of your main beam to the intended user. At the same time, you want to focus this null angle into the other users. That way, you are going to maximize your signal delivery to the intended user. You have no interference into this guy, other guys. That's the purpose of SDMA design, which is not easy, right? Because you have to control. So this is because that this is called the beam forming. Okay? Because you are making beam into that guy. And this one, right, is called beam nulling. You are focusing the null angle into that guy. That's beam nulling. So we want to do the beam forming and beam nulling at the same time. That's the best way to do it, right? No interference, at the same time, maximum delivery to him. That's not easy. First reason, these guys are moving around. Second reason, this guy can be anywhere, and the angle between these two is kind of arbitrary, and there are so many users, and it's very hard to keep track which angle, where is this guy, right? So it's not easy to do it. Anyway, the concept of SDMA is like this. Okay, focusing the energy to the intended user. At the same time, you want to minimize the interference. Okay. The last thing is the OFDMA. This is by far the most popular frequency, most popular multiple access scheme these days. This OFDMA, in fact, as the title says, it's the same as FDMA, almost similar to FDMA. Okay? Only difference is that this is orthogonal FDMA, but this is anyway FDMA. And what was the FDMA? This was not the FDMA. Each users are separated. All the users are separated by frequency. Each user has a different frequency. That's the FDMA. Okay? However, what is different is that, let's go back to FDMA here. In FDMA, users are separated by frequency, but in order to make enough separation, in order to avoid interference, what we have to make sure is that we have to have enough guard band between each user's frequency, right? This guard band is kind of waste because you cannot do anything here, right? You cannot transmit anything. Okay? This is basically waste, complete waste. So therefore, it's not very efficient. Okay? We have like a 1 megahertz of bandwidth. You can only have like a couple of users because of all those guard bands. Now in OFDM, that's the difference. In OFDM, it looks like this. So all the users definitely have each of them, each of these narrow band has no guard band in between, and not only that, they actually overlap. Okay? So compared to this one, right? It's definitely much more spectral efficiency, higher efficiency, because now we squeeze all these things. Even though you deliver, let's say we have 10 of them, we call each one of them as a subcarrier. So we have 10 subcarriers, same here, 10 subcarriers. But with the 10, in order to have 10 subcarriers, maybe in this case you have 1 megabps, 1 megahertz. In this case, you can have only 600 kilohertz. So therefore, you can have only a small, you can squeeze all these things into small range of frequency. So somehow this one has much higher spectral efficiency. Okay? Because the spectral efficiency is defined by bps per hertz, right? You divide by hertz. So if you have a small size of hertz, if you need only small range of hertz, definitely you have higher spectral efficiency. So that's OFDMA. Now what we have to understand is that how is this possible, right? Each one of these subcarriers are overlapped. Okay, now how is this possible? That's what we have to find out. So first of all, there is a pros and cons here. What is the good thing about that is, again, the high spectral efficiency. And also, what is very fundamentally very important is that this OFDM, OFDMA and OFDM, those two are same technology, OFDM and OFDMA, basically same thing. Technology-wise, it's the same. That allows you a simple equalizer. Okay, very simple equalizer, because we apply the frequency domain equalizer. Traditionally, equalizer is done in time domain. Okay, why is that? What is the purpose of equalizer? Equalizer is trying to remove inter-symbol interference. Inter-symbol interference is what happened in time domain. Okay, so traditionally that was the problem. We talked about the telephone modem last week, right? Once technology advanced in telephone modem, they actually put it stronger and stronger equalizer, okay, in order to remove more and more symbol interference. Okay, that's all done in time domain. But here in OFDM, we do that in frequency domain, and advantage of doing that in frequency domain is that it's much simpler. Okay, we'll talk about that. And also, this is one pros, one advantage, and we'll talk about it in a minute. But there is some problem. There's some disadvantages of using OFDMA. One is that it has high peak to average ratio. We call it as a PAPR, power, high peak to average power ratio. It actually has a power here, PAPR. Okay, that's one problem. But this problem cannot be solved. At least the clear solution about high peak to average problem has not been known so far. Okay, so we have to go with it at least. There are a lot of research papers, a lot of research scientists. They investigated PAPR and they approached it. They proposed some scheme to reduce it, but there's no clear solution so far. Another problem is that this system is sensitive to frequency offset. Okay, we'll talk about it in a minute. Let's look at a block diagram of OFDMA system. Okay, here's some block diagram picture of the OFDM. Initially, here is your data to transmit. We have a serial data input. And here, it's a bit level. We have a bit. -1, 1, 1, -1, things like that. 1, 0, 1, 0 kind of thing, right? This is bits. All this serial bit information now goes to this block, and this serial bits becomes parallel. Okay, we make a parallel to serial to parallel converter. We simply put it in parallel, and the size of this, so make a vector. Okay, make a vector. So in the serial bit sequence, now we make blocks like these blocks. Okay, and one block we make a parallel like this, and next block and make another block like this. Okay, that's how you do it, block by block. And the size of this block is going to be n. And n is the size of FFT and IFFT. Okay, we use FFT, IFFT in here in OFDMA. Still bits. Okay, and these many bits now goes into signal mapper, and signal mapper is same as modulator. Okay, we use modulation, of course, right? So for each of these bits, you use like a BPSK. But if you use, let's say, if you want to use a QPSK, then each of them is 2 bits. 2 bits here, 2 bits here, 2 bits here. In that case, we need 2n bits, 2 times n, because we have n line here, right? So you need 2 bits for each, so 2 n bits if you want to use QPSK. Okay? So anyway, you use modulation here. Once you do modulation, we get symbols. Each of them is a symbol. Now the complex value. This complex value now goes into IFFT. What is IFFT? Yeah, the inverse Fourier transform basically convert frequency domain to the time domain. So what that basically means is that we were in the frequency domain. Now we want to go to the time domain. Okay? This is like a frequency domain system. But any system, right? When you go out to the channel, it has to be time domain. When you go to the channel, right? Just before the channel, we have to go to the time domain. So therefore, up here, right, in the system, you can go to time domain, frequency domain, several times. That's okay. Eventually, before going out, it has to go to the time domain. So here in the OFDM system, we do the whole frequency domain processing. We do the modulation, these things. We do the in frequency domain. And that is not in this picture, but typically we do the coding also, right? Channel coding, like a convolutional coding and all these things. That's also done in here, in frequency domain. So all this modulation and coding, all the baseband processing is done in frequency domain. Eventually, after all these things, you get the frequency domain symbols, okay? Complex value. That goes into I50. Now you get the time domain samples. That is again parallel because we do the parallel processing. We make it simply serial, then go out to the channel. We'll talk about this one in a minute. But anyway, go to make this one as a serial symbol sequence, then you transmit. Now that transmitted block, that block goes through the fading channel, right? And then received by the receiver. Once you add it cyclic prefix, now you remove the cyclic prefix. Okay? And then this is serial symbol sequence. You make a parallel. Similarly like this, right? Make a parallel and put each of the symbol, now put that into the FFT. Okay? This one was the time domain. Now we want to go back to the frequency domain. So make a symbols here and put that into the FFT. The output of the FFT would be n symbol, another symbols, right? Not bits yet. These are still symbols. And those n complex value or n symbols now go into equalizer. And this equalizer is in frequency domain because we have done already FFT. Okay? Now we do go to the equalizer. Why do we need equalizer? Because we had a fading channel, right? Okay. So we have equalizer, and this is called the one-tap equalizer. Why do we call this one-tap equalizer? Is that this equalizer has just one tap. Typically equalizer, think about the telephone modem and any equalizer you think about, equalizer is like a filter. So equalizer therefore has many taps, many filter taps. But this OFDM equalizer, you have only one tap. So that's why we call it as a simple equalizer. Okay? So we have one tap equalizer. You get the symbol, still symbol. Now those symbols go into signal demapper. This is the demodulation. Okay? Once you do the demodulation, you recover bits. And these bits, still in parallel, now go into serial. That's what you receive. That is supposed to be same as this one, ideally speaking. Okay? So encoding, decoding is done here, typically, right? Because there's an encoder. What's the input? Input is a bit sequence. What is the output? Another bit sequence, right? Only the size of bit sequence is now getting bigger because you added redundancy. But in encoding or encoder, decoder, input is a bit sequence, output is another bit sequence always, right? So here is the range of bit. So you have encoder here, you have a decoder here. Okay? I skipped it here, but anyway, here encoder, decoder. So that's the whole process of OFDM. A. OFDM and OFDM-A. In fact, this is OFDM actually. Okay. Now let's think about this bit. Each of these sides is now getting larger. Okay. And this large number of each of them is now getting bigger and getting bigger once you do the signal to parallel. And that goes into the modulation. Now get a symbol and go to the FFT, IFFT. Okay? And then this is transmitted. So once these symbols are now going to the IFFT, so therefore it goes to the time domain. All this information are mixed in time domain. Okay? Therefore I just make it colorful like this. Right? So what I'm showing you here is that this was original symbol duration right here, but it actually is getting bigger here. What does that mean? What that basically means is something like this. Let's say you just transmit this one. Forget about OFDM. You just transmit this one. And now let's think about that. Our channel condition is like this. We have a channel delay profile like this. So in that case, this is the delay spread, this much. And our symbol duration is only this small. So therefore, this is what? Frequency selective condition. Okay? We are talking about frequency selective channel condition. Remember the frequency selective channel? If the delay, this delay, the channel delay, it's much shorter than the symbol duration, that's a frequency flat. Okay? Relatively, if this delay is significantly large compared to this symbol duration, that's the frequency selective. Because you transmit this tiny symbol over this channel, then you have echoes. Okay? And some of the echoes will now affect the rest of the other symbols. That's a symbol interference, inter-symbol interference, right? So in this case, definitely, if you transmit this one in the channel, that kind of channel, there will be an inter-symbol interference, right? So therefore, this is the frequency selective channel. Now let's think about the OFDM. In OFDM, you do not transmit each bit like this. What you do is that you make it parallel, and using the parallel, you make each of that is now is getting bigger. It sounds a little bit strange when I say it's getting bigger, but let's think about this way. Forget about this picture, this one. Let's just make it parallel. In that case, this size is still small, like this size. That goes into the frequency domain, the time domain, right? By FFT, you get the time domain. And after all that, eventually you get the parallel to stereo. So eventually you go to this way, serialized symbols, right? The size of this symbol, once you've done all this, the size of this symbol should be same as that symbol, right? Because this one was the size of the original symbol. Even though you do all this processing, anyway, the size should be same. And this size is same as that size. However, domain here is different from that domain. We were in the frequency domain. This is now in time domain. So thinking about the FFT, IFFT, each of these frequency domain symbol is now spreading all the symbols in time domain, right? That's what happened in the frequency domain and time domain. Each of these symbols is now getting spread over into the whole symbol here, right? So therefore, now you think that this piece of information, okay, this piece of information is now being spread all over. Therefore, that basically means that it's almost same as each symbol is now getting bigger size. So once you do that, now what we can effectively get is that each symbol, since we are doing serial to parallel, each symbol is now getting bigger. Therefore, channel never changes. We have this delay. Now we have this much symbol duration. Therefore, our channel becomes now frequency flat. It was a frequency selective if you transmit this one as it is. But by doing the signal to parallel and doing all these things, now we actually change the frequency selective channel to the frequency flat channel. That's the most important thing why we use this OFDM system. Okay? You can make the frequency flat channel. Channel will never changes, right? The channel characteristic is the same. However, whether it's frequency selective or frequency flat depends on your symbol duration. Okay? Because it's a relative value. Right? This one never changes, but by changing the definition of your symbol duration, make it smaller one to bigger, we actually make the frequency selective to be frequency flat. Typically, right, think about the frequency flat scenario. Frequency flat always, generally, frequency flat is like a low bit error rate, right? Because your symbol duration is big, therefore it's going to be slow, right? Slow system, slow data rate. Here, it's not. You have a high data rate system, but by putting each of them in parallel, that's what is important. We actually transmit each of them in parallel. So each one is now going under the frequency flat. In here, we put all this together, that's frequency selective, but by putting into parallel, now each symbol is getting larger. Therefore, thinking about only one symbol, now it's a frequency flat, right? Because this one is much larger than delay. This one also is much larger than delay. So each of them is frequency flat. So we make a channel to be frequency flat, but what can be achieved here is that we transmit all these symbols in parallel. Each of them is frequency flat, and we transmit multiple in parallel. And parallel. Each of them in parallel in different frequency. This one, we go into the different frequency, right? In frequency domain, each one is loaded into different subcarrier. So each one is delivered using different frequency in parallel, and each one go through the frequency flat channel. Okay, that's what happened. Now, what is a good thing is that why do you want to make a frequency flat? By the way, I just said that we made the frequency flat. Why do you want to do that? Why do you want to make it frequency flat? Why not just frequency selective?
Equalization.
Yeah, that's why the equalizer becomes simple. So once you become the frequency flat like this, right? Eventually think about the receiver. Eventually you do the reverse step in receiver. This is what is transmitted over there. You receive that. Right? And you undo these things. You take the FFT, go back to this one. Eventually you recover these things, right? But when you receive it, it's not going to be the same as this one because of the fading. But since we are talking about the frequency flat for each of them, right? What was the frequency flat? In frequency flat fading, remember that in frequency flat, we can always use the simple model like this, right? You transmitted some symbol that goes through the fading, and you add a noise, that's what you receive. This simple, you can use this simple model for frequency flat. Frequency selective, this model is not valid anymore. You have to think about something like this, right? In frequency flat, because there are some symbol interferences. So you have to use this kind of model for frequency flat. But in frequency selective. But in frequency flat, you can use this model. So therefore, in equalizer, what you need to do is simply you multiply H inverse. That way, you multiply H inverse to receive symbol. Y is what you receive, right? You simply multiply H inverse. Therefore, you multiply H inverse here, so you cancel out these two. So therefore, you get the X. This is what you eventually recover in frequency flat, right? So therefore, in frequency flat, equalizer is just simply 1/10. Okay, that's why in equalizer it's going to be just 1/10. And not only that, this is a frequency domain. Okay, it is frequency domain. So in the receiver, these things first has to go to FFT, now go back to the frequency domain in receiver. Okay, then you multiply the 1/10 equalizer, because that way now you see the frequency flat. Right? Go back here. That's why we have an equalizer here. That's going to be, since we are thinking about the frequency flat channel, we just simply cancel out the H inverse for each of them. Each of them has different H, right? Each of them has a different H. Do you understand? Each of them has different H, because each one is a different frequency. Each one, we are talking about, here we are talking about the frequency domain, right? We have n frequency subcarriers. Each one has different H. Why is that? Because that's what I show you here. Right? That's exactly what I'm showing you. These are n parallel subcarriers. Each one has a different H, right? This one has a good value of H. This one has a very bad value of H. Each one is H. Each one. Different H. Each subcarrier has different H, right? So therefore you apply the difference equalizer here. Each one is 1/10. When you just cancel out the H inverse for each of them. OFDMA is popular, as I said, and examples in the practical system is like this. You see the OFDMA in wireless LAN, also some European digital broadcast system, audio broadcast, also some of the cellular, recent 4th generation cellular systems. Thinking about the evolution of cellular systems, 2nd generation, we call this 2G. 2G cellular systems were divided by two technology. One is GSM, which is like a European standard. The other is a CDMA. Part of the CDMA, actually CDMA was partly used in some part of the USA. Okay? And when it evolves, go to the 3G, 3rd generation system. Everything now is converging to CDMA technology. 3G, everyone uses CDMA. Okay? Even that, there is some European approach, and there was some American approach. But anyway, technology-wise, 3G, they use CDMA. Now, the 4th generation, 4G, is being commercialized, right? Recently, you probably heard about LTE in TV commercials and things like that, right? So that time is near, is coming, right? 4G, all the 4G, 4th generation cellular technologies, they do not use CDMA anymore. They use OFDM. Okay, every 4G cellular systems, they use OFDM. Okay, so now the whole technology has changed. I didn't talk about one thing here, which is this one, cyclic prefix insertion here. Okay, so let me quickly talk about that one. Okay, so as I said earlier, in this system, right, here is the original bit sequence, okay, and we make blocks, right? I make a block and block, and each block, which has a size of n, I make a block and put them in parallel, and another block and then put it parallel, right? So I make a block like n size, okay, and make it parallel and do all these things, and eventually you make it again parallel to serial, you get this one. The last step before you go to the air is the cyclic prefix insertion. And the cyclic prefix is actually you copy the last part, copy that and paste it into here, into the front part. And this is why I call this a cyclic, because it's like rotating, right? It's cyclic. You copy this one, the last couple of samples, and put that into the front, like this. So that's a cyclic. Why do you want to do this? That way, your actual symbol becomes larger, right? You make a larger symbol, larger symbols. That's what is actually go over there. Why do you want to do that? Have any idea why? Important thing here is that the whole OFDM is block by block processing. Okay? Even here, every bits are serial fashion. We make a block and make it parallel, and this parallel block goes for process, and the next block is independent, right? Next block come here and do its own process. Okay? Even here it was a serial fashion. Now it's a block processing. So what we have to make sure is that one block should not interfere with the other block. Okay? Because each block has independent processing. Okay? So that's what we have to make sure. One block should not interfere with the other block. Okay? Because once that happens, that cannot be undone. That cannot be recovered. Okay? So in order to do that, right, you have to reserve some samples. Okay? You have to make you have to put some spaces like this. Why do you need this space? Because of this one, right? We have this much delay. When you transmit this symbol, now because of this delay, we have echoes. So this whole thing will be echoed here, here, here. And if the next block comes right after it, then this symbol should have echoes. That echo will interfere the next block. So definitely we don't want to do that. So that's why we reserve some place. Therefore, this region, which called the cyclic prefix, this prefix, cyclic prefix, should be larger than this one in order to absorb this one. Okay? And in the receiver, of course, you receive the whole thing, right? And then what the receiver should do is simply cut it, remove it. Because this portion will absorb this one, interference, so that will be discarded simply. But that's why we need this. Okay? However, in that case, right, why not just make it 0? You can do the 0 pairing, right? Because anyway, those parts will be discarded, and you can just make a placeholder for this one, right? Why not put in 0? Why do you want to make it cyclic? Because if you put 0, right? Now what's happening is that this one is some signal. Now 0. Signal. 0. So that kind of your signal is not continuous in that case. This is like sudden change of your signal in time domain. So if you have some signal, smoothing signal, and suddenly 0, and suddenly you have another signal. Well, that kind of sudden change of your signal makes your frequency spectrum to have a very high undesired spectrum. So what I'm saying is, if you put in zeros here, right? In frequency domain, this is your frequency spectrum, and if you have zeros right there, then that actually makes spectrum like this. You have some unintended out of band signal that will appear. Okay? Typically, when you have that sudden change in time domain, that's a very bad idea of your signal. Give me any reason. Give me any example. You probably heard the signal shaping, right? There's a technique called the signal shaping. Okay? Why do we have a signal shaping? What is the signal shaping, by the way? We always say that we transmit bits. Let's say this is 1, 1, minus 1, 1. We simply learn that we transmit this information just think about the basic transmission system, okay? Not this kind of thing, just simply basic one. So you transmit 1 minus 1, 1. Okay? In that system, you do not transmit this one as it is. Because why? Because this one is actually sharp transition. That actually makes your spectrum have a spike. It's a very bad idea. No one actually do that. What you need to do is that if you want to transmit this one, you have to apply signal shaping for this one. Okay, you have this one, and this goes through the signal shaping. Now, what the signal shaping does is that you make this signal have a smooth transition. That's what the signal shaping does. You have to shape the signal. That way, your signal has a smooth transition. Okay, you definitely have to do this. That way, you have a very clear spectrum. No, it's different from quantization. Yeah. The quantization should be done before that. And before going out to the air, you have to do signal shaping like this. Similar idea. You don't want to put a 0 because that will have a very bad impact onto your spectrum. Okay? So that's why we put in cyclic. When you put the cyclic, then actually you have the some smooth transition of your signal. Therefore, it's very good for your spectrum. So everyone does that.
But if the cyclic width is 0 as well, then the gates will rise the same.
That is true, but this one potentially have a very, very little probability to be 0 because you are not transmitting 0, 1 as it is, right? 0, 1 was here, and you do the modulation, and go to the frequency domain. Once you go to the frequency domain, every sample is now the sum of the addition of all these time domain samples, right? So here, the only cases that you have 0 here is that you have some symbols here that actually do the multiplication, addition, and the whole processing activity, and somehow you get a 0 here. Okay, that's the only possibility. But even that, you may have maybe 1, 0. Even having 0 is very low probability, but still, even you have it, you probably have a 1, 0 here, but all the others should be okay. Okay, because we are talking about the time domain, frequency domain kind of thing, right? You do not have a 0, 1, things like that here. Okay, typically you have a very, very fluctuating, complex value here. In fact, this signal right here looks like if you put the oscilloscope, right? If you put the oscilloscope right here, then the oscilloscope will show you this kind of signal. That's what you will see. Okay? This is why we earlier said that OFDM signal has this problem, peak to average power ratio. Okay? That is why. What is this one, by the way? Let's think about some other conventional system where you just transmit 1 minus 1. In that case, your power, your signal will be like this, right? For example, let's say this is what you transmit. I'm thinking about another system, simple system. In that case, now let's think about the power. Power is a square of this, so let's flip this one. The power is something like this, right? This one has almost a constant power. Okay? So this one has no PAPR problem. However, in this signal, in OFDM system, now let's think about the power. The power is fluctuating like this, right? So therefore, average power is somewhere here, and the peak power is here. So ratio between these two, peak power divided by peak average power. That's this one, PAPR, peak average power ratio, right? This one is definitely much higher than 1. We want to make this to be 1. This system, the PAPR is 1. But this system, this PAPR is much, much higher than 1. This is very bad one. But in OFDM, we have this problem. Okay? So that's why we need a cyclic prefix. Okay, a couple of more slides. This is about the random access. What is random access, by the way?
Accessing the channel.
Yeah, why do we call this random access? Why do we need this?
If I have to transmit something,
Huh?
I will go. If I have something to transmit, then I will go for the channel.
Okay, should that be random?
Because it depends on the channel. When it's free, then you will get. It's not sure that you will get. Because if busy, then you don't have access. And then you may not have again. So
I may not have data to send all the time.
Yeah, that's kind of makes sense. It means no synchronization. What is a synchronization? Synchronization basically means that base station and all the users agreed into a certain time. Okay, that's a synchronization. That's the first thing to do when you power up your cell phone, right? You power up your cell phone. The first thing to do is a cell search. Your cell phone is busy finding the cell, okay, finding the base station. Once it finds the base station, the second thing to do is the synchronization. Okay? Let's talk about the basic of synchronization. Synchronization is something like this. Let's say I buy a new watch. Okay? This one shows a random time. I cannot use that as it is, right? It's useless. Because it is watch, it's not an, this is just watch, but I have to make this time to be exactly correct. So there should be some reference. Okay? And I have to, to change this time to match with the reference, right? So that's a synchronization. So now let's think about this one. Base station has its own time. And when you power up your own cell phone, you have your own time. Each one has different time. Okay? So which one should be the reference? Base station always should be the reference. So base station never changes its own time. Okay? It is fixed. You cannot change it because there are thousands of users. How can the base station match with all of yours, right? Well, users have to change their own time to match with the base station time. Okay? Base station is always a reference. Now the question is, as a user, how do you know? How do you change how do you know that, how much time I have to change in order to match to the base station time? There's offset, time offset, right? How do you know? That's why we need the synchronization process that typically relates to the correlation, autocorrelation, and things like that. Okay, there's a certain process. But anyway, that's a synchronization. Once the synchronization is done, that basically means that your time and my time is matched. That doesn't necessarily mean that your time and my time is exactly correct. Okay? This one is what you need to remember. Let's think about the synchronization, original definition of synchronization. Okay, this is base station time. Okay, I have some time like this. Okay, whatever it is. Maybe this is the time, some time for symbol, or this can be just 1 second, doesn't matter. So base station has its time like this. Okay, let's say we have user 1 and user 2. And let's say the base station is right here, and user 1 is near here, user 2 is far away. Okay? Now the user 1 and user 2 wakes up at its own and arbitrary time. You just power up any time, right? Now you do the synchronization process, and let's say synchronization is done. Let's say this is an uplink case. When you do the synchronization, you have to do the uplink synchronization. You also have to do downlink synchronization. Okay? We have to do the two different synchronization because uplink and downlink are independent. But now, just to give you an idea, let's think about only the uplink. Uplink, maybe downlink first. Yeah, we'll talk about uplink also. Let's say we think about downlink because that's what you have to do first. Downlink is what the base station transmits. Okay. Once the user 1 and user 2 are synchronized, that doesn't mean that user 1 and user 2 are synchronized right here. Okay? User 1 is here, user 2 is here. That's not the synchronization. Why is that? They should not exactly synchronize in this manner. That's not the synchronization. What is the synchronization exactly is that this guy, the base station transmits some information, right? And this user 1 will receive it. But this distance is very short. But user 2 is far away, so it takes more time to deliver that, right? Considering that propagation delay, we want to make these two are synchronized. Therefore, user 2, okay, have this time here, using this, considering the propagation delay. The user 2 has this time here, using more propagation delay. So that is synchronization. That's what we want to do. In fact, only God knows this one, right? User 1 never sees this one, right? User C never receives this one, because now the base station transmits some signal, synchronization signal. User 1 receives it, right? Maybe a little bit later, user 1 receives it. User 2 will receive it a little bit later because it has more propagation delay. So what user 2 can see is only this time. Okay? Only God knows where is base station, where is user 1, where is user 2. So this picture only God knows. User 2 never knows where is exactly time. This user 2 thinks that this here is this one. That's what user 2 think. You see what I'm saying? Yeah. So that's synchronization. I'm drawing this picture as a God's perspective, okay, just to help you idea. But user 2 thinks that here, this one and this one is matched exactly, but that's actually not the case. That's user 2 and user 1. That's how the synchronization is done in downlink. Now let's think about uplink. In uplink, here is again some time duration, time instant. And user 1 is synchronized. Then what that means is user 1 has this point in here, in user 2. Why? Now let's think about it. User 1, this is the starting of my symbol. I want to transmit the symbol here. This is my symbol duration. Now I transmit here. At that time, then it actually has some propagation delay of this one. And by the time the base station receives it, this is the time. So this is the propagation delay. So in order to deliver your packet to the base station at this point, you have to transmit a little bit early. Because there's a propagation delay, right? You have to transmit a little bit early. Same way here. User 2 is far away. Okay? So in order to make sure that your packet is received by base station at this point, you have to transmit much earlier. Okay? Considering the delay, right? So that's what happened in the synchronization. So therefore, user 2 will always has a different time synchronization for downlink and uplink, right? Same way. Every user has a different point of downlink and uplink synchronization. Base station has the same. It never changes. It has exactly the same time for uplink and downlink. It never changes, but each user has a different synchronization. But now, this is the synchronization step. But let's say we have no such synchronization. In that case, user 1 and user 2 have absolutely no idea how long is the delay, propagation delay, and when I transmit. It has no idea. Okay? That's no synchronization. Now considering uplink with no synchronization, that's an even bigger problem. Because the base station the multiple users are trying to talk to one base station, but there's no synchronization. Each user just transmit anytime it wants. So that's the case of random access. That's why you call this a random access. Each user pick a random time. Okay? So this problem actually has been known like 1950s or 60s or sometime back. At that time, the Aloha protocol, okay, is proposed. So that's the first protocol that is proposed in that time. So this Aloha protocol basically means that user 1 just transmit at random time, okay, and user 2 transmit its own random time. So if these guys are unlucky, since no one knows what happened on the environment, if they are unlucky, there may be a collision, right? Once a collision happens, then from the base station perspective, base station receives the garbage because these two users, talk to each same time. So these are mixed together. You receive garbage. Okay, so that's what happened. So once the garbage is received, then they basically wasted whole time, right? So base station basically tells them, okay, I didn't receive your information correctly, so please do it again. Now then, what happened is they start to do it again, then they may collide again, right? Because there was a collision already. That means these two users have something to transmit. They are waiting. So whenever the new slot opens, they do it again, right? Another collision. So in order to avoid such things, what they do is that they do a exponential backoff. Exponential backoff. What that means is when they realize that there was a collision, they run a random generator, and they toss a coin, okay, in the random. They may throw dice, something like that. They actually run the random generator, and they get the random number, and based on that random number, they wait some exponential delay, okay? If the random number gives you 0, then you can go ahead, you can transmit immediately. But the random time gives you like 1, then you can wait some number, some time, maybe 2, then you can wait another longer time, something like that. So by each one, since each user run the random generator, probability of the colliding is less. Okay, so that's how they are trying to avoid, probabilistically sense, they try to avoid collision. But pretty simple, actually very simple, right? What people realized a little bit later is that let's put some slot concept into the Aloha rather than just a pure random. What we can do is that we can make a slot, okay, time slot. And which time slot you want to start, that can be random. So here in this slotted Aloha, it's the same as the previous pure Aloha. The only difference is that now we have a concept of slot, and you can choose random slot. Okay? But you cannot start at the random time. You have to start only at the start of any slot. That's the only difference. But from the starting time, it's like a discrete, right? You can start only here or here, here. It's like a discrete. You cannot start the transmission in any arbitrary point. That's the difference in here. Then by doing this, you can actually reduce number of collision. Okay? So that's what they do. They do exactly the same as the exponential backoff. You probably heard about the CSMA somewhere. Okay? It's important to remember this terminology. This is very popular even now. Carrier sense multiple access. What this means is a carrier sense. What is a carrier sense?
Signal on the channel, we are just sensing it. If you're getting some energy level, you decide that there's
Yeah, something like that. Before you transmit, you first hear. Okay? You first listen to the channel. Okay? looks like there's nothing, then you can jump in. Okay? You first listen, and looks like someone is using it, then just hold it. That's what they mean. Carrier sense first, before you transmit. Okay? But this is not a perfect solution anyway, because let's say multiple users who are listening at the same time, okay? And at that time, no one was using it. So a lot of people, you realize that, okay, channel is empty. So everyone suddenly jump on at the same time, okay? There is a still probability of collision. Okay, that's what this picture shows you. Okay, user 1 was using this one, okay? And user 2 wants to use it, but it listened first here, and looks like someone is using it. And user 2 realize that the channel is busy. So you hold it, and you try to attempt to listen again here, and now the user 2 realized that the channel is empty. So now it starts to transmit. Okay, so that's what it shows you here. It says the several CSMA strategy. One persistent, non-persistent, P-persistent. What this means is that the persistent here means the probability. Okay, one persistent basically means that whenever you listen to the channel, and looks like no one is using it, then you can jump in with the probability 1. Okay? You can try to use that with the probability 1. However, think about the P-persistent. Okay? What that basically means is that when you listen to the channel and no one is using it, then now you can run the random generator. Okay? And this random generator will tell you that now you can jump in or you can still wait. So the probability, even you realize that the channel is empty, you can start to transmit with the probability P. That's what that means. Okay? So what that means is even though the channel is empty, you don't want to transmit right away with the probability 1. You can transmit with the probability P. Okay? So the reason of doing that is to avoid the collision. There is a tech strategy called the CSMA-CD. So there is some additional CD. So collision detection. Okay? We have a CSMA, but in addition to that, there's a CD. That's actually pretty popular. You probably hear this one in many times. If you go some other maybe seminar and things like that, you probably hear about CSMA-CD. This picture shows you an example. User 1 was transmitting something. Okay? User 2 listened and realized that the channel is busy because user 1 was using it. So he back off and wait a little bit more, right? And by the time now user 3 has something to transmit. Okay? Now the user 2 and user 3, they listen the channel right here, and both of them realize that channel is empty now. Okay? So they jump in and transmit. So those are unlucky, right? It's because they actually accidentally they realize the channel is empty, so they transmit at the same time. Eventually that was a collision. And now the collision detection basically means that you transmit here, and user 2 also transmit here, and when they transmit, they also listen its own transmission. When I transmit, I basically listen also. Okay? When I transmit. And when you transmit, and at the same time you listen, like a listen while talk, right? When you listen it, now you listen a collision. Because when you listen it, then you listen both voices, right? These two guys are transmitting, so therefore you are listening some garbage because these two are combined, right? But when you transmit and when you listen together, you are only listening your own. You transmit what you transmitted, right? You know what you transmitted. So you transmit at the same time you listen it, and you listen whatever you transmitted only, then that's okay. Because you are the only one using this channel. but you transmit something at the same time you listen, but you listen garbage, that means there is a collision. In that case, since there is a collision, you just stop it immediately, right? Because anyway, it's collision. So you are wasting, if you just keep transmitting, even with the collision, you are wasting more and more time. That becomes garbage anyway. So when you detect the collision, immediately you stop it. Even in the midstream, you stop it. And then you do a back off. And then try to do next time. That's the CSMACD. Any question so far? Okay, see you next week.